Good morning, everyone, and thank you very much for joining us for today's webinar, Continuous Insulation Compared Within 6 Steel Stud Framed Wall Assemblies. My name is Shalika Sivathasan, and I am the Administrative Assistant in the Continuing Education Department at the OAA. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and who are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. Before we begin, I would like to share some important information to ensure an effective and professional webinar experience. Please be informed that this session is being recorded for quality and educational purposes. For accessibility, we provide automated closed captioning service available in multiple languages to accommodate the needs of our diverse audience. In order to maintain a stable internet connection, we have muted all participant microphones and disabled video feeds. Kindly note the chat function has also been deactivated. However, we do highly encourage engagement through our Q&A window, which you will find at the bottom of your screen. Feel free to submit any questions you may have for our speaker there. Questions will be addressed during the designated question and answer period at the end of the presentation. For those seeking continuing education learning hours, please note that attendance is crucial. A minimum of 80% attendance is required for these hours to be accredited to your OAA transcript. Please just allow a few weeks for the processing and reporting of these hours. And lastly, please note that the presenter does not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. Now, I am excited to introduce our speaker for today's session, George David Schoenhard. George has over 45 years' experience in designing fine architecture, with the last 10 as the principal of DSS-Philly, one of the leading high-performance building envelope consulting firms in the Philadelphia region. George has also branched out to Canada with his DSS Ottawa, and he brings his decades of architectural experience to skillfully advise, design, implement, or remediate building envelopes on behalf of other architects, owners, contractors, and as an expert witness. George is the inventor and developer of the high-performance black lattice wall design with its US and Canadian patents, and he actively researches comparative building envelope assemblies, speaking nationally at the IIBEC and ABAA. So please please join me in welcoming George Schoenhard.
Here we are. Good morning. Good morning. Thanks, Shalika. So, good morning to you all, and welcome. We have a nice showing. We're about 80 participants, which is great, and it's growing by the moment here. So we're going to be talking about continuous insulation, and we're going to be talking about non-combustible construction using steel stud framing. Continuous insulation, to work with continuous insulation, we need to know what our climate zone is. Well, it's interesting. The other day, I looked at the what were the temperatures at that particular moment, and in climate zone 4, which is what Philadelphia is, it was 4 Celsius. And in climate zone 5, which is Toronto, it is 5. I'm sorry, it was 10. In climate zone 6, which is Ottawa, it is 5. In climate zone 7, which is Sudbury, it was -1. And up in Big Trout Lake, way up there, in climate zone 8, it is -2. So it is very interesting. In Ontario, you have 4 climate zones, and actually climate zone 5 for Toronto happens to be the same climate zone of much of Pennsylvania. So with that, let's get started. Let's see now, make sure I hit the right button here. Come on, wake up. There we go. Here are our goals for the day. We're going to start talking about making sure that we're clear of what are the code requirements within OBC and then also within ASHRAE that are related to the non-combustible and the steel frame and the continuous insulation. We're then going to take a look at the 6 assemblies and their rationale. We'll kind of explain through them what are their standard features and what are some of the challenges of them that we have to be aware. We're going to talk about how to avoid some problems. Sometimes putting more insulation can actually become a problem because it traps moisture and it traps condensation, or it creates condensation where you don't want it. And then we're going to take a look at some WUFI models that we did a few years ago and comparing the hygrothermic characteristics of the 6 wall types. And they are designed for climate zone 5, which happens to be Toronto. So with that, here are the 6 walls. And we will come back to this particular view multiple times. So as you see this slide pop up, it'll kind of be the introduction into the next section. So in order to do the comparison, I had to kind of come up with the rules of the game. And in order for there to figure out what are we comparing to. So here are the rules. We're going to be working with OBC. We're non-combustible. We're use group C. I could be other use groups, but for this exercise, it's use group C, which happens to be residential, and we're sprinklered. We're commercial steel stud. The cladding, and this is interesting, the cladding is independent. That means left, right, independent of where the studs are. So that means basically where you attach the cladding is not dependent upon where the structural stud is behind it. We're going to be using ASHRAE 90.1 as our energy guide. We're going to be using climate zone 5. The reason for that is climate zone 5 is the first climate zone that requires the vapor control. Any zones less than that, they're too warm and they don't require vapor control. So everything within Canada requires vapor control. And for the outdoor cladding, we're using 1/4 inch fibrous cement. And for the inside, we're using mold resistant drywall. Now, from the overview, we're going to take a look at the OBC and only those particular categories and sections of the code that are relevant to what we're working on here. We're going to start by looking at part 3, which is fire protection. And these are the categories that we're going to be looking at quickly as we go through. And then after that, we're going to take a look at part 5, environmental separation. So for non-combustible, we better understand what is non-combustible. Well, there is a definition for it, but the definition also relates back to what are the testing standards, because that really is what determines whether it's flammable or not, or whether it's combustible or not. So in terms of combustibility, you're using the S114 test, and then there also is another set of tests that uses the S135, which is the cone calorimeter. So this basically is what tells you whether or not it's combustible or non-combustible. Now, with that, there are certain numbers of things that are allowed, even within non-combustible construction. There's a little caveat there. There's certain aspects of it, I call it minor combustibles, and the code refers to it as minor combustibles, that are allowed. And that is very helpful because there's certain things you just plain need to be able to do. So for instance, the spray foam sealant that goes around the window, that's excluded. The caulk, that's excluded. The air and vapor barrier, they call them sheathing papers in this particular section. The vapor barriers are allowed. I like to try to keep those membranes below flame spread 25. And then also the wood blocking is allowed to be technically combustible in the non-combustible construction. Now we're going to get into the first section here is because we do have foam plastic as some of our wall types. Well, what is the issue with foam plastic? Well, we have to keep in mind here, yes, it is permitted. Now they said it's okay if it's under a flame spread of 500. That's really high. At this point, you can buy the foam easily within a flame spread of 25. So you want to try to bring that down as far as you can. The higher it is, the more flammable it is. So anyway, flame spread 25. But it is permitted. The other thing is it needs to be protected to the interior, except if it's up in like a attic space or a concealed space. So it needs a thermal barrier to the interior. And typically it's drywall. It could be lath and plaster, but there are not many folks that do lath and plaster anymore. It also could be masonry or concrete, or it could be through you always give you the ability to go through testing. If you have some unusual or alternate arrangement, you can basically prove its viability through testing. Now, what happens if it is a prefabricated foam panel? They are available, and some of them are quite good. And I've used them on multiple projects. But let's find out, what are the requirements for that? Well, number one, it says if you're going to use it, the building needs to be sprinklered. These have to have a flame spread of less than 500. Again, I think that's extremely high. Keep it down, flame spread 25. Building has to be less than 18 meters. But it's not allowed in use groups B or C. Well, I happen to have chosen that this exercise is going to be done in use group C, residential. So thus, I can't use the prefabricated plastic foam panels, but there is a way around that. Now, they also say there's not supposed to be an airspace, sheet metal facing on both sides, tested per 138. But we are allowed to use a mineral fiber core panel. And those are very nice, and that's what we're going to use in our exercise. Now, I'm sure you're very familiar with this, with all the different use groups. And as I said, we're going to use residential. And it's use group C. Now, this is a really handy chart. And so I really like this section. You learn a lot of information of what you need to do in this. So we are looking at this one particular area in group C, which is the residential. And we are allowed group C, any height, any area. We have to sprinkler. And it requires non-combustible. Now, if we were smaller or lower, we could be in wood frame or heavy timber, but we're not. We're purposely, for this exercise, we're bigger, so we need to be non-combustible. There need to be floor separations and load bearing. Where there's load bearing, it needs to support the supported assembly. Those are structural issues and fire rating issues. Now, what happens if we put a foam panel on the outward side of the sheathing? Let's think about that one. Well, first, the code is going to say, all right, you're allowed to put foam on the outside of the sheathing, but only if you're allowed to have a certain number of unprotected openings, which means if you're right up against you're right up against a property line, they're not going to want you to be putting foam plastic on the outside of the building. So that's the one item. If you are more than 3 stories high, then obviously if you're less than 3 stories, you have some more flexibility. If you're over the 3 stories, foam plastic shall have exterior protection. All right, so now you're going to have to put something in front of it to protect it. You're going to have to be either put concrete or masonry. So yeah, that makes sense. You can put rigid foam like in a brick cavity, and you can put brick on the outside. That's done all the time. Or you can put a non-combustible material on the outer side of that plastic foam. So effectively, the sheathing is going to act as that outer protection. So effectively, what the code is saying is don't put the plastic foam on the outward side of the sheathing if you don't have something that is more like, for instance, masonry or concrete on the other side of that, outward of that. So you can't just have foam there and go ahead and put the 1 inch, the 1/4 inch fiber cement board in front of it. Not allowed. So that's important because that affects our wall designs here. Now we're going to talk about environmental separation. What are the energy code? What are the R values and the U factors? Well, it works a little differently in the Ontario codes. They go off of climatic loads, which is out of the SB1, via calculations. That's a little different than what I'm used to. I'm used to looking at a chart and it tells you what the R's and the U's are. So, but they also say you can use good engineering practice. I like that. And they refer to the ASHRAE handbooks. Good. Out of the ASHRAE handbooks, they refer to the ASHRAE 90.1, which is the Energy Design Guide. So let's move on. The OBC requires an air barrier. Air barrier is basically what an air and weather barrier is, a WB, air and weather barrier. Also, the W could stand for water resistant barrier. Sometimes in the field, everybody calls it AVB, AVB. It's easier to say, but it's absolutely wrong. You are not trying to get an air and vapor barrier on the outboard side of the wall. So it's AWB. Now, what is the purpose of the air barrier? It's basically to slow down air leakage. And you're allowed to use it in the assembly. It could be a material, it could be the assembly, it could be the type of material it is. It needs to be continuous. It needs to include the control joints, the expansion joints, the transitions, the penetrations. So it isn't just the coating. It isn't just the membrane. It's the linkages between things. And at this level of construction, we're talking about a class 1, which is 0.06. Now, we also require vapor barriers. If we have a differential temperature or a differential vapor pressure, well, there's nowhere in Ontario you're not going to get a differential temperature or a differential vapor pressure unless you happen to be, I guess, an open building or an unheated building. But typically, for the most part, everything that we do is going to require a vapor barrier. So we're controlling the vapor diffusion. And I don't like the or in there. I like the diffusion, but also you need to be able to allow the venting once the vaporization needs to continue in the outward direction. Now, I do really like here that they talk about to minimize the accumulation of condensation. They're accepting the fact that in certain weather conditions, could be just hellaciously cold. You're going to get some condensation, temporarily condensation, but we want to make sure it's temporary. It has a way to vaporize, it has a way to get out, and it has a way not to destroy the materials on a long-term basis. Now, they also say it's okay if you use the interior wall finish. Problem with that is it's not always there. People start hanging pictures on the walls. You cut in an electrical box, in which case it's not always ideal in terms of that interior vapor. Now, this is where the climatic conditions come from. It's out of the SB1. Now, SB1 also refers to the ASHRAE handbook. So we go to the ASHRAE handbook. The ASHRAE handbook says good engineering practice, fundamentals, and it refers to the ASHRAE 90.1. So again, here we are, we're back to the 90.1, which is frankly what I'm used to using. Now, a few other items here, and then we're going to get right into our wall types. Prodemnity, if you happen to be insured through them, have made it very clear that they are not insuring water ingress unless you've made some provisions for it. And it's the water ingress coverage requirements. Basically, they need you to be designing rain screen principles using a primary and secondary plane of protection, which is what we're doing in all of these designs, making sure that it can dry and making sure there's at least a 3/8 inch airspace in there and positive drainage so that when there is condensation, it's able to come down, be captured, and then drained out. All of that is excellent. So let's just keep that in mind. And then here's the 90.1. In this case, it's not in the code. So we're using it as a standard. It's a reference guide. Now, by climate zone, as I said right at the very beginning, Toronto is climate zone 5, Ottawa is 6, Sudbury is 7. This tells you basically what is the R value and the U factor requirements by that climate zone. And it refers to it as non-residential, residential, and semi-heated. So we're going to be using the residential section. So in climate zone 5, under this particular code, which is, well, this happens to be 2022. This is like the brand newest one, is an assembly U value of 0.055. Or you can do prescriptive, which means you just add up the insulation layers, but you're not able to use the air films and the air spaces and those kinds of things. Just prescriptive, which is R13 plus 10, which means 13 between stud, 10 is your continuous insulation. Now, what is continuous insulation? 90.1 has a definition for that. It's uncompressed. It's continuous across all structural members. So it's not starting and stopping for the studs. It's keep on going. It's without thermal bridges. And there's a few caveats there. Other than fasteners and service openings. So you're allowed to have the fasteners that hold the wall together. And the continuous insulation can be either located on the interior of the wall. I'm not sure I would do that, but anyway, the interior of the wall, the exterior of the wall, or somehow integral to it. We'll talk about that a little bit. Now, the other thing, well, because back here they said without thermal bridges, continuous insulation without thermal bridges. All right, what is a thermal bridge? Thermal bridge. Thermal bridge basically is the path of least resistance for energy. If it can't get through the insulation and there happens to be a spot that allows faster transfer, boom, that energy is going through there. So that's what we're looking for. That ends up becoming the bridge. The bridge is like, all right, it's a little path and the energy is going through that thing. Now, the Clearfield bridge, that is basically saying the studs and the girts, they're calculating that in the efficiency standards of the insulation. So for instance, when you look up at bad insulation in a steel stud wall, it's basically saying, depending upon what the spacing is, you're either 40 to 60% efficient. So basically they're deducting the energy loss that's going through the steel. That's if you're using the U factor approach. And that is captured in the efficiency factors. Fasteners are excluded. Linear thermal bridges, you need to be sensitive to those. Those are slab edges. Those are the shelf angles that hold the brick up. Now, let's go look at the R's and the U's. Toronto, as I said, is 5. Ottawa, 6. Sudbury, 7. I originally designed this thing under IECC 18. And so it has a slightly lower R factor than what it is currently right now, because it was just a couple of years ago, but things are always changing. We're also going to look at this with ASHRAE 2019, and then also we're going to look at the high performance, which is the ASHRAE 189. So this was originally designed under when the insulation was 7.5 was the continuous insulation in climate zone 5. That now has been increased to 10. Notice the between studs stays the same. It's the continuous insulation that increases. Climate zone 6, Ottawa, that goes up to 12.5. Sudbury goes up to 15.6. If we use high performance, starts out at 12.5, goes to 15, goes up to 18.8. So what's changing in all of these is the value of the continuous insulation. That is where the most, that is, well, number one, it's like 100% efficient, and that's where the best energy efficiency is in order to make these walls perform. Now, let's get started with our 6 walls. We're going to start with, I call it the typical Z. Typical Z is basically steel studs, and you're able to calculate this with the prescriptive method, which is basically there's insulation between the studs, and there is mineral wool on the outward side of the sheathing. Now, what are the strengths of this? It uses common materials. They're easily available. There's nothing special order here. Encloses very quickly. So the wall can be made watertight very quickly. It's free of the 134 requirements, which means it doesn't require special fire testing. Now, what are some of our challenges? Well, in my opinion, there is thermal bridging here. That galvanized steel Z cutting through the mineral wool, to me, looks like a thermal bridge, because the back leg of that Z is effectively touching the leg of the stud, except for, I don't know, a little bit of insulation value for the gypsum sheathing. So it's not ideal. But anyway, unfortunately, this is an arrangement that's done fairly often, but it always drives me crazy when I see it because I'm worried about those Z's, the galvanized Z's sitting there. There also is bat inefficiency. That insulation sitting between the steel studs, you're losing a lot of efficiency when it's in that arrangement. There are condensation risks because moisture can basically get trapped or it can occur, dew point can occur within the body of that insulation, in which case then it actually will condense on the inward or the cavity side of the gypsum sheathing or on the side walls of the studs. So there are condensation risks, and we'll see some of that when we look at WUFI. Now, there's also an issue that the semi-rigid mineral wool on the outward side, it's great as long as it stays dry, but when there's condensation that occurs or when there's water that's leaking through the rain screen, a rain screen is not 100% waterproof. There's this, I don't know, 5% water can get through it, in which case there's a little water back there. And in the summertime, there can be condensation that occurs back there. So anyway, there are opportunities for that insulation to get a little damp. Now, the other problem in this is you can't super insulate the bad insulation. At a certain point, it's just too thick. You don't get enough temperature drop across that insulation in order to help drive the moisture out. So it just kind of sits there. It's like having too many blankets on. It just actually becomes a problem. Now, here's an improvement on this. We're still able to go prescriptive here because we have between stud insulation and we have continuous insulation. But this is different because we use a composite Z. It's made out of a few materials. Sometimes it's fiberglass. I refer to it as a composite Z. Also, it uses spray foam. And in this case, it's closed cell spray foam, which is kind of the best way to go because the closed cell acts as the vapor barrier. There is no bridging. That composite Z is actually more energy efficient than the insulation that's on either side of it. So that the Z in this case, because it's composite, is not acting as a thermal bridge. And the spray foam is controlling vapor movement in both directions. So in the summertime, it's controlling the vapor movement, trying to work its way in towards the air conditioning. And in the wintertime, it's controlling the vapor movement on its way out towards the cold, dry air on the outside. And you can super insulate, not a whole lot, but you can insulate to the point where you want to make sure that the dew point is occurring within the body of the rigid insulation. And because the rigid insulation is closed cell, you're actually not going to get water particles occurring at that point because moisture can't get there. So the temperature's there, but the moisture's not there. Now, what are some of the challenges with this? There are plastic foam requirements. So you have to make sure that the drywall is on the inside, and you also have to make sure there's some sheathing to the outside. Now, you also have to buy a special Z. This is not commonly available, so obviously you need to special order it. And you can get moisture that occurs between you can get moisture that occurs at the mineral wool where the mineral wool is touching that horizontal Z. Well, you can say, wait a minute, why don't you just put the Z vertical? Well, you can. And actually, I like it that way. But that's not the way we designed the exercise. The exercise was we needed to be able to locate the cladding independently, left and right. If you run the Z's vertical, that Z is on the stud, so now you have to control where the studs are. That's fine, you can do that, but that's not how we set up this little exercise. So here's our first poll question. And I will read the questions. And Shalika brought it up so that we can kind of see how you are, which way your thinking is on this. Now, we're going to use each of these as a learning opportunity. Bad insulation versus spray foam. They act the same. Composite Z is a clear field thermal bridge. Open cell versus closed cell. Closed cell. Outward semi-rigid mineral wool insulates even if it's wet. There happens to be one answer that is the most correct. And what do you think? And we'll use this as a learning opportunity. Shalika, are the answers coming in?
Yep, they are.
We have 107 of you out there. That's wonderful. So let's see how the answers kind of come in on this. Bad insulation versus spray foam. They act the same. Look at that. Closed cell versus open cell versus closed cell. Make sure you use closed cell. And that is effectively the most correct. Now let's go look at the other ones. Bad insulation versus spray foam. They act the same. They don't. The reason is because with bad insulation, there's air that is basically being trapped by the glass or mineral wool fibers. So it really is acting like a blanket that you wrap around yourself. There's air that's kind of stuck between all the fibers. With air comes moisture. With moisture, you hit the dew point, it's going to start changing from vapor to a liquid. So we have to be careful when we're working with bad insulation. With spray foam, particularly if it is, well, let's just say strictly, if it is closed cell, it is keeping the air from actually passing through. So thus no air, no moisture, no dew formation. Now, Composite Z is a clear field thermal bridge. It is not. With the Composite Z, it is not acting as a thermal bridge. It is actually, as I said, it's just as efficient as, or even more efficient than the insulation that's on either side of it. So it's not acting as a thermal bridge. Open cell versus closed cell, you want to use closed cell. Open cell basically, number one, it's way more flammable. The other thing is it lets moisture kind of work its through. And the other thing is if it gets wet, it sucks up water. So it's not ideal. Closed cell. Last one is outward semi-rigid mineral wool insulates even if wet. Well, there's a bit of debate on this, and the answer is basically if it is damp or wet, it loses its insulation value until it re-dries. Once it re-dries, the insulation value comes back. So where in this, now, yes, the mineral wool or the fiberglass does have coatings on it. It's not supposed to suck up water just like a great big sponge. But as an example, where that mineral wool is touching the horizontal Z-girt, there's the possibility the fibers are going to get wet there. Where it is pushing up against something, there's the possibility that moisture is going to kind of hang out there. If it's hanging out there, it gives you the possibility that it's going to absorb there for a while. So that's the first poll question. That's fun. So let's move on. Our next wall type, and we are right time-wise, we are right on schedule. So I'm going to keep moving here. And I just have to make sure I make the slide live again. Now we're going to go into wall type 3. Wall type 3, this is the one, this was a real challenge. Now you have to calculate this off of U. It doesn't follow the prescriptive method anymore because effectively all the insulation is outboard of the structural stud. It also says that that panel is the outward sheathing. The panel is the sheathing. Okay. Well, we can't use XPS. That's out. Now, it would be protected to the inside, but it's not protected to the outside. Can't use phenolic. Not allowed in Ontario. Can't use phenolic. Foil-faced ISO? No. Why? Well, number one, we couldn't use it because we chose to work under residential. So now what we can do is we can use tongue and groove to form mineral wool panel. That is a product. It is manufactured. Tongue and groove, the panels come together very nicely. Another nice thing about that is there's a metal facing on both the inside and the outside. That acts as a vapor barrier. Now, what are the challenges? That mineral wool panel, that fabricated mineral wool panel, that's a lot more expensive than an ISO panel. I don't know how much, I just know it is. Now, the other thing you have to be careful when you buy a prefabricated panel like that, the outward face can be vulnerable during construction. Things happen during construction. Machines hit it, stepladder hits it, scratches occur, so forth. Basically, that outward face is vulnerable. Sometimes the joints are also not completely trustworthy. I always like, if you're going to do that, to make sure that the joints are double sealed. The prodemnity is also going to want to make sure that you have double seals in these things. So there's always a certain built-in redundancy that's there. But still, even then, there are certain locations where there's just too much coming together. And sometimes it kind of starts to fall apart. Not in an ideal situation, but I'm talking about real world, the way things are actually constructed. So one advantage or one possibility is you adhere an air barrier face to the outward side of this. So basically it overcoats the joints, it protects the face of the panel. Make sure it's adhered. It's not just a flappy sheet. You want to make sure that if it's a flappy sheet, you're going to get, it acts as a pillow and you're going to get moisture that's going to occur behind the membrane, and that's not where you want it. So it's basically acting as an additional coating on the face, and it's effectively almost acting as a third membrane on those joints. So that air barrier, yes, it is an extra step. Now, this panel, just like this, does have some limited fire rating. You may need to put gyp sheathing on the inward side of that. And let's go to this next one. Next one is when you have a magnesium oxide panel bonded to urethane, and that is applied directly to the studs. And so it acts as the sheathing panel. There's no gyp sheathing. It's called basically all-in-one, a CIS panel. Structural insulated sheathing is another acronym for it. It does definitely enclose quickly. It acts as a fastener base, which means if you put a fastener into it, theoretically it holds. So thus, anywhere on that panel face, you can apply the cladding tracks for the rain screen cladding. And it's all 100% outward insulation. Okay, super efficient, goes up fast. It manages the vapor movement through it in both directions because the urethane foam is closed cell, so it's not letting moisture through it either way. And what's nice about this is you can do quality control before you ever put the cladding on. So basically the building is buttoned up and watertight before that cladding ever goes up there. And you can also get some fire rating options. You may have to add another layer. You may have to put a layer of sheathing behind the board up against the studs, or then that's typically the route that's done in that case. Also can be prefabricated. And you can add some additional bad insulation in the stud cavity. Not so much that it moves dew point back into that cavity. You definitely do not want the dew point occurring inboard of where you're able to trap the moisture. So you have to think about that. Sometimes more insulation is not better. Now, here's some of our challenges. You can't over torque the screw that you're putting in. It'll pop. The material is brittle. So when you put the screw in, you have to put it in very carefully and not over torque that thing. Otherwise, you're going to strip the threads. It is a specialized panel. This isn't just readily available. And you may have to put some gyp sheathing in behind it in order to increase your fire ratings. Here's our next poll question. Shalika, here we go. I will read them. Now, the sheathing is not needed to the exterior of foam. That's the first. Next one is mineral wool, a mineral wool clad panel with only outward metal facing is okay. Next one is extra air and weather barrier on prefab panel is advisable. Next one is fastener base holds just like plywood. What do you think? Sheathing not needed to the exterior of foam. Depends if you're a low-rise building or not. What we were doing is we were going up higher, non-combustible construction, residential. And in our case, we did need to put some kind of sheathing or non-combustible to the outward side of that foam. Mineral wool clad panel with only outward metal facing is okay. That's a tricky question. The If it's just metal, it's going to rust or it's going to corrode. Now, a lot of times it's pre-coated. That's better. But then again, it still can get scratched. So I tend to encourage an extra layer of weather barrier out there. Next one is extra air and weather barrier on prefab panel is advisable. And fortunately, yes, that is, most of you did come up with that as well. And the fastener base holds just like plywood. Yes, the fastener base does hold. And yes, if you put the screw in properly, it holds just like plywood. But the problem is you can strip the threads really fast. If you over torque, it strips the threads because the material is very brittle. So from that sense, it's not just like plywood. Plywood is very forgiving from that point of view. Okay, we are going to move on. All right, come back live again. Here we go. Now, we're into the last two. This one is done often on institutional projects. It's clip and rail. It's basically where the jip goes on, the sheathing goes on the outside. There's either spray foam, in this case, there's spray foam on the back side of it. You could put some bad insulation in there. The air and weather barrier is on the face of the sheathing. Then there's a clip and rail system. Then there's mineral wool that's out there. And it has all sorts of fire rating possibilities. It easily can be a 1 hour wall, a 2 hour wall. It also has flexibilities in terms of the weight of the cladding systems. So this is, if you're going to put a stone panel on, this often is the system that's used with that. There are a lot of steps, though, in the construction of this. And in the summertime, there's active condensation out there. That metal is collecting condensation. And so you have to make sure that you're sealing the fastener holes and the attachment plates, because we don't want water hanging out right up against the air and weather barrier. The air and weather barrier is meant to allow water to move past it. It's not waterproofing. It's not meant to just sit there and hold water right up against it. There is moisture holding. Where that mineral wool touches all these metal components, there's the possibility that the fibers are going to collect water right there. And it's multi-step construction. There are a lot of steps that get moved that have to happen in order to try to build this wall. Now, and here's the last. It's called back lattice or back crisscross. And this is basically where the sheathing, the insulation is inward of the sheathing, but it's also outward of the structure. Now, it's accomplished by basically coming up with a crisscross framing between the studs vertical and a crisscross to you, that direction. And in this particular case, it does use common materials. And there's a framing lattice. So basically, you have to build this crisscross frame. Once you build the crisscross frame, there's a thermal break in this particular design. There's a thermal break. There's a little thermal transmission pad that goes between the horizontal to the vertical, which is what you kind of see, that beige colored little block there. That's not a piece of plywood. It's a piece of rigid foam, very high density rigid foam. Now, with this, it works very well with a two-directional moisture flow because it's using closed cell foam. There's no moisture holding in it. The quality control is done at the outer side. Basically, this is called a naked wall, which means that all that insulation is inward of the sheathing. Once that sheathing goes on and it's water and the joints are sealed and it's sealed to the windows, you have a watertight wall. And you can do your quality control testing then at that point. And it does require that special thermal pad, and you have to be careful at the framed openings. So take some extra framing and a little extra protection at your window openings. Now let's look at the WUFIs. We're in our last section here. And again, we are right on time. What we're looking at in WUFI is Where does the red line is the temperature. Now you can see it basically starts from the inside where it's warmer, and it goes to the outside where it's colder. And we did 4 seasons, so it is basically early in January, middle of March, early July, and early October. And this is for climate zone 5, so it would be Toronto. And what we're looking at, and this is for wall type 1, which is where it was bad insulation between the studs, sheathing, mineral wool on the outward side with the horizontal Z-girts, galvanized Z-girts. So let's look at this. Where the temperature comes down to the point where it meets the dew point temperature, and they happen to touch. There, right there, is the location where condensation can occur if it happens to be on a material that will support the change of state, basically between vapor to a liquid. So it's not going to occur out in the middle of the puffy insulation. It's going to occur when it's either on the sheathing or on the metal stud, where, boom, that's where that energy transfer happens, and that's where the little particles of water occur. Now, right there in January, you can see that there's some, it's touching, but this also happens to be on the outward side. It's within that outward cavity. Let's go take a look at March. March is interesting because you're getting into the shoulder seasons. Warm during the day, it's cold at night, goes back and forth and back and forth and back and forth for a while. So sometimes you got the moisture working its way in, sometimes you got the moisture working its way out. So we still have that point of right there where we have some condensation that's occurring. That happens to be on the outward side of that insulation. Now, it's not going to occur on the insulation, but it's going to occur on the metal components, such as that Z-girt. Now, does it matter? I don't know. It's way out here. What difference does it make? Well, you can make your insulation wet at a certain point if it just keeps staying there. And in this case, the moisture is building up. Now, we're going to look at this blue line. If we're to the point where condensation is occurring, and I forgot to move the little things here, so we have, I'll try to catch up with, whoa, back up. Here we go. So condensation is occurring here, and moisture is building up. Well, where is it building up at? It's building up out here. All right, so what we have to be careful with is that the fasteners, to make sure you seal them carefully. So you put a bed of sealant on before you put that fastener on, or you'll put a line of sealant around the top of the attachment plate or across the top of the Z-girt so water doesn't go sliding in behind that thing. Now, here's the other thing that's interesting. Let's take a look at July. Now, we're talking about bad insulation. In July, moisture flow now is working towards the inside. You can actually see now, see how the red and the purple line are actually pointing to the inside. They're not pointing to the outside anymore, pointing in. Take a look right here on the back side. This means the cavity side, the insulation side of that aluminum foil. It is very close to hitting the conditions for dew point to occur, which means water could theoretically occur on the cavity side, the insulation side of that foil. That's not a good place, because also the foil happens to have a piece of paper that's connected to it. So then the paper can get wet. If it gets wet and it's paper, it can turn to mold. So that's not an ideal condition. Let's go look at the next one. This is where we have the spray foam on the backside of the sheathing. We still have the same mineral wool on the outside, but now we have that fiberglass Z-girt that's occurring there. Let's look in January. These things never touch at all. No issues there. March, very nice, all the way through. Now, where are we at? That's March. July. All right, from here to here is July. Right, this is when moisture now starting to basically vapor flow is towards the inside. Right at that gypsum panel and the air barrier on it, there is, looks like I hit the right button rather than the left, sorry. There's some moisture that's occurring. There's condensation that's occurring at the air and weather barrier. And yes, it builds up to a little bit, but here's the point. It doesn't linger there long. And the other point is that we need to make sure that you're using a vapor permeable air and weather barrier. You do not put a vapor barrier or a vapor barrier type air barrier on the outward side, so that when that moisture is here, it is a chance to vaporize. Next time the sun comes out, warms up the wall, vapor goes out. Now let's go take a look at the next wall type. Oh, we're into a poll question. Okay, this is our last poll question. Foil-faced bat in July shows high risk. Next one, spike in moisture at sheathing means use a vapor barrier, air barrier. Next one is spike in moisture at outward mineral wool is no issue. Next one is dew point inward of the air and weather barrier is okay. What do you think? Foil-faced bat in July shows high risk. Yes, it does show high risk. It's because the moisture is trying to drive its way in. And with that, it's warm outside and it's cool inside and it's air conditioned inside. So the humidity, that the vapor density is down. So the vapor drive is inward. And that's good. Excellent. Thank you. Next one. So yes, the foil-faced bat in July does show high risk. Now, that's also why if you super insulate the wall with like lots and lots of bad insulation, having that moisture there now is a challenge, because now the next time when the sun comes out, it tries to warm up the wall. It takes a long time for that heat to get all the way back to the point where it encourages that moisture to vaporize and move out. So it can just kind of linger there. So that becomes a problem. Spike in moisture at the sheathing means use the vapor barrier version of an air barrier. No, please don't do that. We're in Canada. The vapor barrier is on the inside. If you were in Miami, vapor barrier is on the outside. You're not. Vapor barrier is on the inside. You don't put a vapor barrier as the outward air barrier on a building. Now, the last one is a spike in moisture at outward mineral wool is no issue. Well, it's not technically an issue for the mineral wool, but the problem is it's the components around the mineral wool. It's the metal components. It's the Z's. And it's the fasteners and the little back leg. You can't have water hanging out. If the water hangs out there, it's going to saturate through the air and weather barrier. Dew point inward of the air barrier is okay. Ooh, no, it's not. Occasionally, you may have some weather condition where that occurs, in which case it's a temporary condition and it will reverse itself. But on a long-term basis, it's a bad idea. You want to make sure that that condensation or that the movement, that air movement or the moisture movement is being collected and moved out. So with that, we are nearing, bring it back live again, sorry. And here we go. Here are our last few. This is when that entire, this is the mineral wool panel on the outward side with an air barrier on the outward side of it just for extra protection. It performs very nicely because it just does. It's continuous insulation. There's nothing interfering with it. It's basically 100% efficient. So the temperature and the dew point occur basically to the point where it's right on the outward side of that panel. Now, that's also why it's important. I think it's important to have little belts and suspenders out there by having an extra air and weather barrier out there, because that is where condensation is occurring. There's moisture out there. Now, and it's building up to something. Oh, and this is in March. This isn't in January. This is in March. So this is swing season. So you're getting a time when sometimes the moisture is driving in, sometimes it's driving out. That's why it's occurring in that outer zone. In November also, it's occurring in that outer zone. Moisture's coming in, going out, and you're in those shoulder seasons or swing seasons. And here is our last one with, this is the bonded all-in-one. Performs very nicely. Now, you have to be careful here because the spray foam acts as the vapor barrier. So as moisture is trying to work its way in, it can go through the air barrier because it's not a vapor barrier, it's an air barrier. And it can go through the gypsum sheathing and it basically stops right at the foam, in which case there's a little bit of moisture buildup within the body of the gypsum sheathing. Doesn't amount to a whole lot, but it's there. You can see it right here. That is why it is super important to make sure that that air barrier out here is vapor permeable. Now, let's move on. This is when we have the clip and rail system on the outward side in the summertime. We're in July. In July, there's condensation that's occurring on the hardware out here. So what? It's outward of the air barrier. And what difference does it make? Well, it only makes a difference if there's water that's being trapped or held between the hardware and the air and weather barrier. So to make sure that you seal it carefully and you also seal the fasteners. You don't want water hanging out there. That's a really bad idea because we don't have waterproofing on here. This is an air barrier. And then we have the last one, which is the back crisscross. Wintertime, no issues. March, little bit of issue, but it doesn't account to anything. It's basically because the foam, just like in the other ones, the foam is acting as a vapor barrier on both the outward, both on the outward side and also on the inward side. So there can become a little bit of moisture buildup within the gypsum sheathing, but again, it doesn't amount to anything. And as long as the air barrier is vapor permeable, the vapor moves on. Summertime, absolutely no issues. In the fall, absolutely no issues. So it's very efficient from a WUFI point of view as well. And with that, we are done. And by golly, we are right on schedule. And Shalika,
Yes.
I'm over by 4 minutes. So that's pretty
okay.
darn good.
Perfect timing. Yes. Thanks so much, George.
Alrighty.
So we are going to move on to the Q&A section. I see there's already a few questions in the Q&A box, but if you do have a question for George, please make sure to type it in that Q&A box now. You'll find that at the bottom of your screen. So we'll go ahead and get started with the first question here. So someone has asked, what do you think is better, concealed fasteners or exposed fasteners on the outside face of the wall?
Oh, let's go look at that. And I think by that, you can see my answer. Exposed fasteners. Now, here's the reason. you can't do a concealed fastener if the panel is only quarter of an inch. In my mind, sorry, quarter inch. I don't know what the metric of that is. You have to get up to about a 7/16 or a 3/8. Again, this is in inches in order for you to have a back fastener. That's a more expensive panel. The other problem, when you put the hidden fastener on the backside, you can strip the threads on that. And so it's a little risky, and particularly hanging those panels up really, really high. I tend to like an exposed fastener. It also goes up faster. And I do like them, though, to be pre-drilled so that you are there's a little bit of movement to these panels around the fasteners because you don't want there to be a thermal stress at the fastener. They do have color capped fasteners. Now, if this is a fancy pants building, at that case, you're going to probably want to use a concealed fastener, in which case then these panels are made ahead of time. There's a cladding track that's used on the back side of it. It's fastened ahead of time. So then you have basically a clip and a rail system, and then you basically take the panel up and it hooks onto the rail, and then it fastens, or there's a little set screw that fastens down below. You would do that on a building that has a higher budget, and that would be typical in that case. Hopefully that answers your question.
Okay, great. We have another question here. So this person is essentially asking, why does it matter if you have condensation occurring on the inside face of the foil-backed insulation when the gypsum board is mold resistant?
Well, in this case, we're in Canada and we're Ontario. We need a vapor barrier. So the vapor barrier, let's go back to that picture. The vapor barrier, boom, 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 boom. Where is it? Where is it? Here it is. Okay, now we could theoretically say, I'm not going to use a foil facing on the insulation. It's going to be an unfaced. That could work. In which case, we could also say that the gypsum is going to have a vapor barrier face to it. And we're going to also make sure that we protect the electrical boxes and control the wall. So basically the face of that inside of that wall is the vapor barrier. And yes, we have mold resistant drywall, and we have that insulation that does not have a piece of foil on it. So now the condensation does indeed have the possibility of occurring on the cavity side of the gypsum. It's not ideal. Also depends on how much insulation is sitting here. If we're going to super insulate that wall, this could be a passive house kind of thing where like more is better. In which case we have a ton of insulation in here. You got moisture sitting here. It can't go that direction because you got vapor barrier paint on here. The only way that moisture can ever leave is to exfiltrate out. Just make sure that if you're going to do that, make sure the insulation, you're not over insulating. Otherwise, that moisture is just going to hang out there, and it may not turn to mold, but eventually it'll rot the drywall. So yeah, there's a nuance there, but the point is that in the middle of the summertime, there is moisture drive that is coming towards the inside.
Okay, great. We have a question in reference to the table SB10 prescriptive table. I'm not sure if that was maybe on one of your slides. But this person...
Actually, an SB10, I'm glad you bring that up because I've been looking for a prescriptive table. So thank you very much.
There you go.
Thank you. In all honesty, I've been studying the OBC here for a year, and frankly, I've been looking for a prescriptive table.
Oh, okay. There you go.
And thank you very much for that.
Yeah, so they have a question. I'm not sure maybe if you can answer this one, but this person has asked, so where the table values show a combination of continuous insulation plus non-continuous insulation,
Yeah.
Do you still conform to the prescriptive path if you propose an assembly that is entirely continuous insulation and zero non-continuous insulation? Or
No.
are you required to prove conformance with a different path in the code?
Okay, that would be, in this particular arrangement, this is prescriptive because you have between stud insulation and you have continuous insulation. And in prescriptive, you are allowed to use the face values of the insulation, basically what's printed on it. So if this says R15, that's what it is. Well, this right there says 15, but it could be 19 or something like that. And then whatever this is stamped out here. Now, let's go to another one where it's clearly different. This one. This is all continuous insulation. This does not fit prescriptively, but it can fit within the category of the U. Now, I'm not familiar with the SB10, and I can guarantee here within the next couple hours I will be. But using the ASHRAE and the IECC, which I'm familiar with both of those, you are allowed to either use prescriptive R or U assembly as your compliance route. If you're going to use the U assembly, then you basically add up all your components: the air film, the air gap, the air film, the gaps, the films, the gaps, the films, the R value of whatever the continuous is, and then there'll be a chart that'll tell you what your efficiency is of the between stud insulation. You basically add those together, you convert it back into a U, and you find out whether or not you are below the required threshold. So the answer to that is you cannot use the prescriptive R if it's just completely continuous insulation. But you can use an assembly U that will allow you to figure out whether you comply or not.
Okay, great, thank you. This is maybe a two-part question. Someone has asked, what is the best system balancing cost and insulation value? And then they've also asked, would you say wall 1 and 2 are the worst systems and wall systems 3 to 6 are preferable?
Okay, let's go to the first part of that first.
What is the best system balancing cost and insulation value?
I really like spray foam because spray foam accomplishes your vapor barrier. It's a moisture barrier. It can be applied on the inside when you're basically the building is enclosed at that point. There are a lot of advantages to it, and particularly in the colder climates, there are a lot of advantages to it. The bad insulation is the absolute cheapest, and that's why it's used so often. I happen to like the spray foam. Now, in terms of the rigid foams or the rigid boards, the magnesium oxide, this is kind of an institutional product, and it's a specialized product. The clip and rail, this is an institutional arrangement. There are a lot of components here, and it takes a long time to put all this together. The mineral one, this one. This is going to be on a more expensive project just because the mineral wool prefabricated panel is going to be a pricey affair. Plus also you have to deal with the joints and so forth. So if we're looking at basically a commodity wall, this and these are commodity walls. This one is with batt, this one is with spray foam, and this one uses the composite Z. And that Z can either go vertically or horizontally. So I don't know if that answers the question, but these are the commodity walls. This is my least favorite, as you can probably tell. This one is absolutely reasonable. and is very easily accomplished and is very successful. Now, what was the other half, Shalika? What was the other half of that question?
Similarly, they were asking, would you say wall 1 and 2 are the worst systems and wall systems 3 to 6 are preferable?
I think I just said wall 1 is the least preferable. Wall 2 is absolutely acceptable. It performs nicely. You do want to make sure in wall 2 that you're keeping the water away from getting trapped in behind that back leg. If you put the composite Z on vertically, that issue kind of goes away, but now you have to kind of coordinate that Z with all of the studs. So there's some coordination that has to take place there. The other ones are more institutional. Now this last one, the back crisscross, this really works well if it's a prefabricated wall, just because you're trying to assemble a stud with a horizontal, and the easy way to do that is when you build them horizontally. So you basically build the wall horizontally, flip the thing up, back spray it, ship it to the site, or you can spray it when it gets to the site. And that works out very nicely as well. Number 5 is definitely institutional. 4, institutional. 3 is, where's 3? 3 is the mineral wool prefabricated panel. That is a more expensive combination by the fact that you have the mineral wool, it's built into a panel, and so it ends up being used on more of, let's say, for instance, a hospital or a medical center, where you absolutely need to make sure that you're non-combustible, non-flammable. You don't want foam anywhere, and it works well for that.
Okay, perfect. Someone has asked about who manufactures the composite girts.
Oh, there are all sorts of people. And I guess we're after program, or are we still on program?
Um,
Am I allowed to cite names?
oh, maybe this person can contact you afterwards if they want to know
Okay.
specifics. I'm not sure. So
All right.
we'll leave that out just for now.
There are about 3 or 4 manufacturers of composite Zs,
Okay, there you go.
but they all have the word some kind of a green in it or
okay.
a smart in it.
Okay. So we'll find out afterwards, maybe. Okay,
Okay.
let's move on to the next question. So someone has asked here, I'm not sure if this is something maybe you can answer now, but they've asked about, or they said they would appreciate practical description on how to seal fastener. For example, your recommendation on slide 39. Is that
39,
something?
39. Let me find it. 39. 39. Okay. So the easy way to do it is, this is clip and rail, which means a clip literally is, it's like a little angle. It's about yay big. It's got a leg on it. And basically, you know where it's going to go on the stud because it has to fasten to a stud. You're going to put a little squirt of sealant. And then when you stick the thing on it, you gush it on. And then you can put a little squirt of sealant in the hole where the bolt's going to go, and you drive the screw through. So now you've protected the plate and you protected the fastener hole. And that's an easy way to do that. Now, if we were, let's go back to one that's a little different, because this is one that rarely does anybody care. They just put these galvanized things up, they screw them on, and they walk away. I was like, oh no. All right, so what happens is the moisture collects behind, it's like osmosis. There's a tight surface between the back leg and the face of the air and weather barrier. Water loves that. That's where water hangs out. So now forever and ever, water is hanging out between these two surfaces. And lo and behold, you've got a screw going through it. And the moisture is going to follow the threads of the screw. and basically it's already broken the air barrier quality at that point. So basically the moisture is going to kind of start working its way in on those screw threads. It starts rusting out the screws. It's a bad arrangement. The better way to do that is basically, this is what that blue line is. You put a line of sealant along the top edge of that Z-girt so that it basically keeps the moisture from collecting there. The other thing I happen to like in this arrangement is you can get a little neoprene pad, and they make them even 1/8 of an inch thick. And you put it on right where the screw fastener is going to go. And then it basically drives through that, and it helps to seal. It also moves that back leg of the Z away from the sheathing a little bit. So now water can kind of slip behind it, and that's helpful. So you basically want to try to avoid areas where things are just jammed tight right next to one another, because water likes hanging out in those kind of places. And you need a little bead of sealant or a little squirt of sealant before you put things together is really helpful.
Okay. Someone has asked, how would you manage fire
I'm going to go
rating?
back. Hold on, Shalika.
Oh, sorry. Yeah, go ahead.
Typically, when you're back in the wall cavity like that, you use air and weather barrier sealant. So sometimes STPE, could be a urethane. There is a version of silicone that's used, but as soon as you start using silicones, you got to be careful what else touches it, because other things don't like to join silicone. So, but there is an air and weather barrier sealant that's used back in the wall cavity like that. Okay.
Okay, great. Thanks, George. So someone's asked, how would you manage fire rating the continuously insulated walls when the studs are load bearing?
The continuous insulation, boing, let's go there. If this is really going to turn into a real honest to goodness rated wall, there'd need to be I think, because I haven't seen this company's design standards on that. Typically, I would think that there's going to be a sheet of drywall, or not drywall, but gypsum sheathing that's going to occur on the outward side of the studs. And you're going to need automatically 2 layers of gypsum back here on the inward side. And the rating, now, of course, you can't just make these things up. These things are tested assemblies. So you're going to have to look through. Basically, the company that makes this stuff has done some fire tests. So you go to them and you say, what are your fire test assemblies? Because you have to have a tested assembly. You can't just make one of these things up. Now, yes, you could theoretically make one of them up, but you're then going to have to go through a fire engineer for them to determine whether or not it works or not. And that all takes time and money, and it might be an institutional project where you have time and money and you can indeed do that. But generally, concept-wise, 2 layers of gyp, it's not as reliant upon the bad insulation. You might need it in order to hit their design standard. And then another layer of gyp here. What is creating the fire rating? Now, in Ontario, the primary focus of the fire rating is from the inside out. The condition from the outside in is only really driven by if you happen to be up against a property line. So it's from the inside out. So that's the direction that you're looking for the fire penetration. That is created by the gypsum sheathing. Sorry, the gypsum wallboard. So effectively, each layer of type X gypsum lasts about 20 minutes. So first in the fire test, the gypsum will just, obviously it gets hot, and it just starts letting off moisture. It's unbelievable how much moisture is actually in a sheet of drywall. But anyway, it gives away its moisture. Eventually then it starts getting brittle and it starts cracking and it drops. Then you got the next layer of drywall. Another 20 minutes, it goes through its whole thing. The paper face burns off instantly. Moisture leaves, starts drying out, starts cracking, and boom, it drops. So now what is left? The studs are staring at you. That's not ideal. So from that point of view, I don't know if you're going to hit 1 hour because you got 20 minutes and 20 minutes before that cavity is exposed. So you may have to put bad insulation in that wall in order to hit an hour rating. I do know with these folks, you can get up to 2 hour, not this folks, where here's magnesium oxide, but you have to put multiple layers of drywall up. And because once that drywall drops, that metal stud is facing the fire. Now it's not going to melt, but it happens to get hot. And as it gets hot, it loses its structural strength. So what you're going to do is, even if we were using this, you would go to that manufacturer, ask them for their fire ratings, their rated assemblies, and they will give you a chart of them that has their the 134s, which is the fire testing, basically what happens when there's fire on the outside of the wall coming through an opening. That basically is the vertical and lateral fire propagation. They're also going to give you the report like the 101s, which is the fire rating from the inside out. So those things come from the manufacturer.
Okay, great.
I don't know if that answered the question or not, but we'll give it a try.
Yeah. So we have a few questions left. We're okay to go a few minutes over time, George, if you're all right to stay behind, so we can hopefully get to all the questions that we have here. So someone has asked, how does having a continuous steel layer, such as a shipping container, affect the dew point? What type of assembly would you recommend for insulating a shipping container building?
Well, you know immediately that the metal of the shipping container is a vapor barrier. So then you have to determine where is it going to occur in relationship to the primary weather line. You could theoretically put an insulated wall assembly on the outward side of the shipping container. So the shipping container is effectively the inside of the wall, in which case the shipping container is a vapor barrier and it's insulated on the outward side. Now, sometimes they don't want to do that. They want to do it the other way. So then the insulation is on the inside. Well, you then have to ask who is using this. So the most efficient way to do it would be to spray foam it, so that the spray foam then acts as the vapor barrier. So effectively what you're doing is you're making a wall that has a vapor barrier on the outside, but then you're putting a product on it that is a vapor barrier. The other thing that's happening is the foam is filling all the nooks and crannies, the little ins and outs of the corrugations. Whereas if you just took a sheet of rigid foam and set it up against the inboard side of the shipping container, you get all these little corrugations, and all those little corrugations are air pockets, and those little air pockets can create a problem. Well, who's using this? Do you really want a flammable product? I know you're going to put a sheet of drywall in front of it, but things happen. Do you really want a flammable product inside a shipping container with people living in there? I don't know. Depends. You can also do an arrangement where you can basically direct apply, spray applied fiberglass. I'm not a cellulose fan, but fiberglass or mineral wool, and basically contain it so that it fills tight to the face of the studs. Put your vapor barrier then at that location, and then, but that is all based on the perfectness of doing it. So if you get moisture somehow going into it, it's trapped, it's stuck. What's a third way? Third way is to treat your container as a rain screen. And you actually have to vent it. So you may have to somehow cut in some flashings, and then you're going to come in from behind it and create basically another wall that is basically the rain screen wall. You'd put like a drainage mat. You're going to basically build the wall from outside in. Drainage mat, air and weather barrier at that point. Then at that point, you can use pretty much whatever insulation you want, because you know the drainage mat is going to collect condensation, and you have a way for that condensation to get out. So that's another way to approach it.
Okay, great. Thank you. Someone has asked here, what do you think about adding batt insulation, and in brackets they put fiberglass, inboard of a 2-inch layer of closed cell SPF in the 6-inch steel stud space? It seems likely that the dew point would be within the SPF insulation layer.
Okay, say that one again. Say that statement
Oh,
again.
sorry. I'm sorry.
I need to get the picture so that I could
Oh,
connect.
no problem. So they've asked, what do you think about adding batt insulation fiberglass inboard of a 2-inch layer of closed cell SPF in the 6-inch steel stud space? It seems likely that the dew point would be within the SPF insulation layer.
SPS, SBS. What is the S?
SPF, they've written?
Oh, spray polyurethane foam. Okay. SBS is a roofing.
Oh,
SPS is spray foam. Okay. 2 inches. Well, that's basically what this is. This is about 2 inches of closed cell spray foam. We have done WUFIs where we're specifically looking at adding the basically an R13 within this zone. Because basically for this wall, and this actually takes us back to one of your earlier questions, for this wall to become fire rated, it's 2 layers of gyp here and R13 mineral wool or fiberglass within this cavity right in here. The R13 or R15, there's not enough temperature drop across the 13 or 15 for dew point to occur within the batt. Now, if you're starting to get up to 19s and 21s and so forth, yes, the dew point's going to keep working its way inward. But 13 and 15, you're within the realm where the dew point is not going to occur within that batt. So it basically sits there nicely, behaves itself, and the dew point occurs, which is where you want it to happen. Is technically the dew point occurs when it's in somewhere buried within the belly of the rigid spray foam, because air can't get there, it never turns to water. And then now that's in terms of moisture going from inside to out. In the summertime, the moisture is going from out to in which case the moisture then is occurring out here on the face of the outward face of the sheathing and on the hardware in which case that's fine because it just follows the blue line. It kind of dribbles down and it gets flashed out. Hopefully that answered that question.
great.
So yes, you can put some batt insulation back here, but not too much. 13, 15, somewhere in there.
Perfect. Okay. Someone has asked, are the thicknesses of insulation shown on the diagrams representative of the R values indicated?
Yes.
Okay. Next question says, you're showing foil-faced insulation in assembly type number 1. Would you recommend a smart vapor retarder that can permit some drying as opposed to one that is entirely vapor closed?
Yes. But I'm not comfortable that that is truly a wintertime vapor barrier. Um, and um, I know it's used. I know there are certain building types where using basically a smart liner like that is fine. Um, and I tend to think if there's really going to be a vapor barrier, it really needs to be real because there's a reason for it. And in the summertime, particularly if you have continuous insulation on the outward side, the dew point in the summertime, you're trying to get it to occur out here. You're not trying to get it to occur in here. Now, if it does indeed occur in here, I guess that's the advantage of having this be more breathable, so then it can kind of continue on in. At this point, I'm more comfortable with a very clear vapor barrier that functions as one. It's a little different though when you're in low-rise residential.
Okay. We have time for maybe one last question. So let me see here. Someone has asked, okay, so they say the air barrier is required to be continuous. Assuming a well-installed continuous AWB, what would you say the impact of a discontinuous vapor barrier is in a very cold zone 7 plus environment? Assuming small openings at electrical boxes, fastener punctures, etc. Would you recommend sealing all VB membrane joints or leave unsealed to permit some drying to interior if vapor were to get into the wall cavity?
Oh, an AWB is vapor permeable. It's an air and weather barrier, air and water resistant barrier. It's not an AVB, which is an air and vapor barrier. So you want something that is vapor permeable, which means above a perm of 10 on the outward side of the wall. That becomes to me, that becomes the primary weather line. Prodemity calls that the secondary layer. I call that the primary layer. So that if there is vapor in the wall cavity, and when the sun comes out, it will exfiltrate out and it will go through that air and weather barrier outwards. Now, if you're up in zone 7, I would encourage you to have a class 1 vapor barrier, which case it means it is continuous. Class 2 vapor barrier is what's shown in this illustration, basically where it's foil faced, but it starts and stops for each one of the studs. So if you're up in 7, it needs to be continuous. It needs to be real. I would even think if you're there, you would put that vapor barrier on the studs, make sure it's continuous. Then you'd put a horizontal furring channels on the inward side. That allows you to run your wires, your conduits, and then it allows you to put your drywall on those horizontal furring, in which case now you're not penetrating the vapor barrier anymore. You have a place to run your utilities. You're not goofing up the vapor barrier. It is absolutely sacrosanct. It is not touched. It's real. And that's what I would do in 7. And typically the codes that I'm used to reading, if there's a class 1, 2, and 3 vapor retarder, and the class 1 is used in the colder climates, then that's definitely climate zone 7 is up in that category.
Okay, great. So I know there were a few questions we didn't get to. Apologies if we missed yours, but someone has actually asked if you would be able to post your email address. Would you mind if we share your email address, or if you
I think
have
you
another
have
way?
it, Shalika.
I do,
You can
yes.
certainly
Yeah.
post it. You
Yeah,
can post it
absolutely.
in
Okay. Great. So we will post that in the chat for everybody. In the meantime, I will just quickly run through my closing announcements. But before I do, again, thank you so much, George, for this excellent presentation. And thank you to all of our attendees for your questions. We had some really great discussion today, so that was nice to see.
It was good. Thank you so much, everybody.
Perfect. A few closing announcements. So again, for those of you who are seeking continuing education learning hours, the OAA will record your participation in this webinar on your transcript. So there is no need for individual reporting on your part. We just kindly ask for your patience at this busy time of year as we process and confirm the accreditation of your hours within the next few weeks. All attendees are going to receive a link to a survey to submit feedback for George and for today's webinar. So we and our presenters highly value this feedback. If you do get a moment to complete that survey once you receive the link, please do so. Our next webinar is taking place next Wednesday, April 8th, with the title Place des Montréalais, Designing Commemoration, Community, and Urban Inclusivity. So this one is a climate action webinar, and it is also free for OAA members. So if you are looking to fulfill your climate action requirement, please be sure to check this one out. And finally, if you are looking for additional ways to get your Con Ed hours before the end of cycle, be sure to check out the Con Ed opportunities page on the OAA website, where we list continuing education opportunities offered by other organizations beyond the OAA. So with that, I will thank you, George, once again for this webinar. Thank you, everyone, for your attendance, and wish you all a pleasant remainder of your day. Thanks very much.